we've just looked at how to do algebra with quite complicated expressions involving exponents. And in all those examples, the exponents were constant, and it turned out that using the exponent laws was a good way to try to manipulate these expressions. So now let's think about scenarios where the exponent isn't constant, and what we're going to find is using logarithms is a more sensible approach in this case. So let's do some examples. I want to do everything here by example, really. So example, find all x. Find all x such that 3 to the power x squared minus 1, so that's in the exponent, is equal to 16. Right, so let's take a think about this problem. So first of all, what do I know? I know that I know that 16 isn't a simple power of 3. 3 to the power 1 is 3, 3 to the power 2 is 9, 3 to the power 3 is 27. It jumps over 16. So there's no real hope of easily spotting a solution here. One thing I notice as well is that the exponent here is no longer constant. The exponent is the variable. And what this means really is I think I'm going to have to use logarithm laws. So I really should use logarithms. So let's take a moment to think about what I mean by that. So first of all, if I have this guy, well, this now, if I apply log to the base 3 of this, it's sensible to do this, right? Log to the base 3 is a sensible thing to do because of the fact it's a power 3 on the left-hand side. So 3 to the x squared minus 1 is equal to log to the base 3 of 16. Okay, so now what do I want to do? Well, I want to simplify this, don't I? And the left-hand side is actually very straightforward, right? So this is now if and only if. So the left-hand side is literally x squared minus 1. That's literally the answer. And why is this true? So maybe I should do the equals first. This is log 316. So this is the definition. This is one of my cancellation laws, really. Log to the base b of b to the c is equal to c. So my fundamental properties. Right, so now what do I have? Well, at this point, life's quite a bit easier. Now I just have to do some much more basic algebra. So now this is if and only if x squared is equal to log base 16 plus 1. And I suppose now x, I could take a square root, but but do I need to be careful about this? I do need to be a bit careful because taking a square root will only give me the positive possibility. There is a chance that, so if I take the square root, I only end up with a positive, but of course the negative would also work. So maybe before I do that, I just want to label the pieces of algebra at each stage. This here is using the fact that a minus b is equal to c if and only if a is equal to b plus c, just that piece of algebra. And then now if I'm going to undo the square, I need to have either the plus or the minus of the square root. So it's no good just having one of the two. And something to be a little bit careful of is, am I taking the square root of a negative or anything like that? Well, no, I don't think so. Log to the base 3 of 16 is it's got to be bigger than 0 because 16 is bigger than 1. 3 squared, for example, is 9. So log to the base 3 of 16 is going to have to be bigger than 2, right? So you're not taking the square root of anything negative. Something as well it's worth saying is we can't really simplify this any further. This guy here, I mean, it's not like 16 is a nice power of 3. So this is a good example of something we know exists, but we can't be completely sure what it is, not by hand anyway. Can't really simplify. Can't really simplify. So there we go. That's a way to solve this. Applying log to the base 3 on both sides was sensible because of the power here being, or the base being 3. Actually, though, that's not strictly speaking necessary. So let me kind of show you a slight variation of this. So observation. So this is pretty confusing when you first see it, but it's important. We could actually have done this with, well, any base really. Do this with any base. It's a weird thing to say, but let me just show you what I mean. So if I take 3 to the power x squared minus 1 is equal to 16, well, I could take any base. Why don't I do it with base 2? Might as well. Let's just see what happens. Log to the base 2 of 3 to the power x squared minus 1 is equal to log to the base 2 of 16. Now there is a reason log to the base 2 of 16 isn't a bad plan, or base 2 isn't a bad plan. It's because 16 is the 4th power of 2. So that means it's going to be fairly straightforward on the right hand side. The left hand side is a bit problematic though. So this is if and only if what? Well, let's remember the following important log law. The following important log law says that log to the base b of a to the power c is equal to c times log to the base b of a. So that exponent being inside can be brought out the front. So that means the following. That means the left-hand side is equal to x squared minus 1 times log to the base 2 of 3. All right, so that's exactly this. And this now is equal to what? It's equal to 4. All right, because of the fact 2 to the 4 is equal to 16. So now I'm kind of in the same type of situation as before, but it's a little bit different. I need to divide through by log to the base 2 of 3. So x squared minus 1 is going to be equal to 4 divided by log to the base 2 of 3. So now this is if and only if. So that's a standard piece of algebra, just dividing through. I'm not going to label that because we've seen it so many times. So x now is going to be equal to, well, exactly the same logic as before, plus minus the square root. This is a bit more of a mess, this way of doing it, but it's not wrong. 4 over log to the base 2 of 3 plus 1. So this and this are actually completely identical. It's not obvious they are, but that and that are exactly the same. Like I said, it's not totally obvious, but it is true. Okay, so very nice. So more of the story, because of this property here, because of that property, the base doesn't matter too much. It was nice to choose base 3 in the top because it was so simple. Like the jump from there to there was really nice, but we don't actually need to use base 3. You could use any base at all that you choose, as long as it's greater than 0 and not equal to 1, because you don't have logarithms for those bases. Okay, so let's do another example, shall we? So find x such that, okay, this one's a bit more tricky. 2 to the power x plus 2 to the power x plus 1 is equal to, let's say, 4 to the x. Now, in this situation, it's very tempting to say, okay, let's do what we did before. Let's just apply log to both sides and simplify, and hey presto. So that's definitely not the correct thing to do. So let me show you why. If I choose, let's say, base 2, it shouldn't matter too much, but let's choose base 2 because it's obvious. So if I choose base 2, apply it to both sides, so that would have to be equal to what? That would have to be equal to log to the base 2, 4x. Sorry, what am I doing? 4 to the power x. So that's true. But the problem now is you can't simplify this. So this cannot be simplified. Cannot be easily simplified. Oh my goodness. In particular, this guy is not equal, as you might pray, to this. There's an example we've seen before. Because if that were true, this would be equal to something really nice. It'd be x plus x minus 1, which is equal to 2x. Okay, and what would it be? Would it be 2x minus 1? So something has gone horribly wrong, right? Well, it's not obvious it's gone horribly wrong, but this is not correct at all. So if you were to replace the right-hand side, the left-hand side, sorry, with this, it's just totally wrong. It is not true. What is not true is the following. Log to the base b of a plus c does not equal log to the base b of a plus log to the base b of c. That's kind of the crucial thing here. Right, they are not equal to each other. This does not work. I cannot easily simplify a sum. So what's the fix here? Well, the bottom line is the laws of logarithms require they require products, quotients, and powers. So to apply the logarithm laws, we can't have sums. We need products, quotients, and powers. So what I've got to do is express the left-hand side as something, not a sum, basically, right? So let's try it. Let's do 2 to the x plus 2 to the x plus 1. Well, I do know some laws of exponents. 2 to the x plus 2 to the x times 2 to the 1. Okay, so this is just my law that says, what does it say? So it's just, I'm just doing it to this. This is the statement that b to the a times b to the c is equal to b to the a plus c. But next, in doing this, there's a 2x factor from each piece. So this becomes 2x times 1 plus 2 to the 1, which is 2. And this is equal to what? This is equal to 2x times 3. So I've taken the left-hand side of my original equation, which was a nasty sum, and now I've expressed it as a product. Because it's a product, I'm going to be able to apply my laws of logarithms. So let's try it. So as before, this is me just looking at the left-hand side. So 2x plus 2 to the x plus 1 is equal to 4 to the x. Pretty nasty example, this. This is if and only if 2 to the x times 3 is equal to 4 to the x. Okay. So now I've got a product, no sum. I can apply logarithms and try to simplify. So now this is if and only if log, let's do base 2. It seems logical, doesn't it? 2 to the x times 3 is equal to log base 2 of 4 to the x. Okay, so now let's start doing my log laws. First of all, I can break apart the left-hand side as a sum. Log 2 2x plus log base 2 of 3 is equal to, I'm going to do one at a time here. I'm not going to simplify too much at any stage. So this is the statement that log base b of a times c is equal to log base b of a plus log base b of c. Assuming a and b are positive, or sorry, assuming that a and c are positive, which they are in this case. So now we can do a bunch more. Let me really just use my laws of logarithms here. So this is if and only if. I've got a power, I can bring it out the front. Log to the base 2 of 2 plus log to the base 2 of 3 is equal to x times log to the base 2 of 4. So this is now just my law of logarithms. I've already mentioned it before. Log to the base b of a to the power c is equal to c times log to the base b of a. It's my other log property. Finally though, log to the base 2 of 2 is just equal to 1. It's my absolute base case, and log to the base 2 of 4 is equal to 2. Right, so this guy is 2 to the 2, and this guy, of course, is just 2 to the 1. So this tells you x plus log 2, 3 has to be equal to 2 times x. Ooh, very easy mistake there. And now I just do completely elementary algebra, moving the x to the other side. This would give me x is equal to log to the base 2 of 3. It's nice to write it that way around. Very nice. So this is a good example of using log laws carefully. We couldn't just immediately attack it from the get-go because it was a sum, but if I cleverly interpreted it as a product, then applied logarithms, I was able to get somewhere. So the conclusion of this is the following, really. When dealing with variable exponents, you want to manipulate, if you're trying to kind of undo exponents and things like this, you want to manipulate into products, quotients, and powers before applying log laws, before applying logs. And manipulate into products, like we did, quotients, that's one of your other log laws, and powers before applying logarithms and logarithm law and their laws. It's kind of a broad statement. It's not completely universally true, but it's something to be aware of. And I just want to really stress the laws of logarithms are incredibly important because, like I've said many times before, you're very likely to be asked to do certain things with specific expressions. And as they are presented to you, it could be incredibly difficult. But if you apply a law of logarithms or something like that, they'll become much more straightforward. So these laws of logarithms are totally vital. Let's do an example, actually, which is very similar to that. So here's an example. So express, let's say 2 log base 2 of x minus 1 minus 3 of log base 2 of x squared plus 1 in the form, so let's do it, log base 2 of a rational expression in x. Let's do that. So this is a rational. So it's a good example, right? Perhaps as it stands, you can't work out what's going on with this function. You need to manipulate it to put into this format. So first of all, let's kind of do our laws of logs backwards. Here, I can see there's a 2 at the front, and I can bring that inside the bracket, right, as a square. It's one of my laws of logarithms, and I can do the same thing with the 3, but with a cube. So 2, so this expression, let's get it. So this expression is equal to log to the base 2 of x minus 1 all squared minus log to the base 2 of x squared plus 1 all cubed there. Right, so this now is me applying the log law, which says log to the base b of a to the c is equal to c times log to the base b of a. That's the log law I'm using here. But now I got a difference. And the difference of two logs is equal to what? Well, this is equal to the log base 2 of the ratio of each of them. And now this log law, of course, is the following. Log to the base b of, well, a over c is equal to log to the base b of a minus log to the base b of c. That's how the logs work for quotients. It's a good example. So we're done, right? We've put it in exactly the right format. This now would be your px over qx. That's a very common use of log laws that you're going to see in calculus. Simplifying things or manipulating things using laws of logarithms. They're terribly important. In fact, really, for things like calculus, finding specific values for logarithms and things like that is not really that important. What matters is deploying log laws to manipulate expressions accurately. So log laws are difficult to use, but there's only 3 of them, right? Remember, there's logs of products, logs of quotients, and logs of powers. That's all you ever use. So if you internalize those, you're kind of fireproof, because that's the only 3 things you need to use ever.